So normally we should be streaming, but doesn't start yet. Okay.
Petite histoire, c'est vrai que je viens de recevoir ton mail, quoi.
Yeah.
Un peu long, quoi. Ok.
T'as de la famille en bas, mais ils savent quoi faire, hein, t'inquiète.
Ok.
Et en plus, c'est pas le drame d'avoir cette place-là. Tu vois, même si les gens rentrent un peu en retard,
C'est pas grave.
c'est pas un souci. Ok, I'm gonna...
So we're waiting for the other 3 members of the
Yeah.
committee.
So maybe, yeah, I will wait that everyone comes in to start sharing my screen, actually.
Il manque encore 3 personnes.
Yeah.
3 members, yes. I'm checking emails in case someone has some issues.
Laetitia is joining us.
Not for the moment, at least.
Laetitia?
Bonjour.
Ah, on t'entend, super.
Yes.
Yes.
Alors, Simon, t'es où?
Ben ouais, je suis à Lyon.
Ah mince.
Ouais, en fait, j'avais sous le posant à la gare.
D'accord. Oh là là.
Ils avaient coupé les fils et tout.
So just so you know, I started to stream on YouTube, like, so maybe it's a detail, but
Le monde me regarde.
exactly.
Ouais.
I think we are still missing Florence and Gabriel.
Yeah. Yes. It's a big
Je sais pas comment on fait pour le couper. Ah, mais toi, tu peux pas mettre sur silencieux, c'est vrai. Oui. On a coupé le tien, je sais pas. Regarde. Ouais, il faut que je mette sur silencieux aussi.
Je sais pas, est-ce que
Eh ouais. Presque, sauf qu'il n'y a pas de rapporteur. Mais...
j'avoue. Mais 53, donc c'est pour ça. Ça me tend à
Il
finir.
y a le temps.
Ils sont pas idiots. Gabriel, Florence, ils passent leur journée sur Zoom, ils savent qu'ils marchent. Ils ont testé.
Tu as essayé le partage d'écran ou pas encore?
Ouais, partage ta slide. Partage la pause.
Ouais, voilà, comme ça.
Yeah.
Tu mets le début de la pause.
No, the thing is like I couldn't. Je vais pas pouvoir les accepter si je commence à partager mon écran.
C'est pas vrai.
Je vois plus.
Quand tu partages, tu peux le faire revenir.
Oui.
Je devrais savoir. Oui, tu peux toujours les accepter.
Oui, vous voulez.
On voit ça.
Juste histoire. Putain, mais tu partages l'onglet là, c'est weird comme truc.
Ouais.
Non, mais voilà. On voit pas la manière.
Oui, mais tu vois pas les slides. Tu vois, c'est pas normal. Tu vas en voir qu'une.
T'as raison, ouais. Tu peux avoir des modalités plein écran. C'est ça,
Fais un F5 pour mettre plein écran.
T'as pas un Chromebook.
Hein?
C'est un Chromebook, il n'y a pas de F.
C'est vrai que j'ai l'impression que quand tu shares, on t'entend plus.
Est-ce que tu entends Cédric là?
Quand je...
Là, je l'entends, mais quand tu partageais le truc, je t'entendais plus.
Oui, je pense qu'il faut que je partage tout l'écran en fait. C'est ça
Mais
le...
voilà, mais partage tout.
C'est ça le problème.
No privacy, Cédric. Hein. Voilà, c'est bon?
J'ai...
Là, on t'entend.
Moi, j'ai...
Ok, ouf, ok.
J'espère que ça se passe
Voilà, là vous voyez les slides, c'est bon?
Ouais, c'est bon, ouais.
Et vous entendez aussi.
Parfait. Bon, tu peux quitter le full screen temporairement.
Ok.
T'as de quoi prendre là, t'as tout. Je prends là. D'accord.
Cédric, c'est un peu subtil. T'as activé le YouTube, c'est bon? Partage sur YouTube.
Normalement, le partage sur YouTube est activé. Et il partage la page du Zoom.
Nico me dit que YouTube marche.
Yes. Merci Nico.
Accepte Florence, peut-être.
Yes.
Maybe you make us mention the people in the meeting. You were just to know each other. Of course, this is the name.
Ah, ok. We also have content here. That's content. That means here.
This is Mark.
Hello.
Hello Gabriel, hello Florent.
Hello.
So good, you're ready.
In around 1 minute, I think I will be. Yeah. People are telling me that on YouTube it's fine, so I think I can start sharing my slides.
Yeah.
I don't know if I have to share audio system. No.
Last time you didn't do it, it worked.
Okay, so don't add anything else.
You can still hear Cédric?
Do you hear me?
Yes,
Perfect. Okay.
and we can see the presentation. There's a couple of minutes.
Let me know when you. So I'm ready whenever you want.
I think you can start. So,
Yeah. Okay, thank you. So we start. Hello everyone, I'm glad to be here today to defend my PhD thesis on optimal transport for graph representation learning. So basically it involves two main concepts to operate on graphs, namely optimal transport and graph representation learning, which I will introduce next before going into the contributions of my thesis. So let me start with the definition of graph data or graphs. In a very broad sense, graphs relates to any object composed of entities characterized by specific interactions. So basically with this definition, you can find graph data in most real-world problems. To give you some natural examples, molecules are graphs, which are composed of entities which are actually atoms which interact with each other using covalent bonds. Social networks too are graphs, as they are individuals who are interacting between each other, whether by communicating, sharing interests, or being friends. Graphs can also be useful as an intermediate representation for complex geometric structures, such as consider a protein folded in a three-dimensional space. You can actually factor it as a graph. Also, you can consider analyzing a continuous system, a physical one, over time by discretizing the system using graph data. So let me introduce this example on the bottom right, where you actually see a fluid system within a box. You consider every subunit of this fluid as entities of your graphs, and then you can look at the interaction, the pairwise relations between the node evolving over time under some perturbations. In the end, all these graphs relate to a simple formalism where a graph is actually composed of two sets. The first one being the nodes, denoted here xi, which are actually the entities. And they are, let's say, at a number n, which relates to the size of the graph. Also, these nodes can be potentially endowed with features, fi, which highlight the specificity of the node. And we assume that they all belong to a g-dimensional space, so that these features can be encoded via a matrix F of feature information. Then the second set, which relates to edges, which are actually the connections between the node of your graph. Here we assume that this connection comes from a function C that assigns to any pair of nodes a scalar value. So in the end, all the connectivity between the nodes can be encoded as matrix C. And for this matrix, you can actually consider many things like adjacency relations, meaning that you could have binary connections between the node, or you can also derive a distance matrix using shortest path between nodes, or any other thing that you can think of. In this thesis, we mostly focus on collections of graphs, meaning that we observe several graphs and we want to be able to process or automate a decision over each graph contained in this data set. So I consider every graph in this data set as GI, a tuple composed of a structure and feature matrices, all with variable sizes. So in the end, the structures, the features, and the size are actually three sources of heterogeneity for your problem, and you have to encode it simultaneously to actually solve the problem or be able to represent anything from this graph data. So basically, it's intuitive that this learning problem is difficult because of these three sources of heterogeneity. And in this thesis, we try to address two main points, whereas the first one is how to factor these sources of heterogeneity for data analysis, understood in a broad sense. And another one relates to the encoding process to predict any graph-level information. For instance, a label associated to a graph or a scalar value in a regression setting, such as when you want to predict the toxicity of a molecule. And in the end, In a broad sense, all these methods in graph machine learning usually pass by what we call graph representation learning, which basically comes down to represent any graph samples onto an embedding space of dimension k, for instance, for which you will have a vector assigned to your graph called the graph embedding. And this graph embedding encodes simultaneously these three sources of heterogeneity for each graph. Basically, this is interesting because from a graph to a vector, you go back to something that is more practical to manipulate. So that's what you aim for, and you want the either structural information of your graph or discriminant aspects of your graph to be encoded in this embedding space. So you have unsupervised learning applications where you want to preserve some properties of your graph or pairwise interactions between your input graphs, so that in the end, directly within the embedding space, you can perform clustering, also try to generate new graphs or complete them if you have a prior structure over them, and other many applications. The second paradigm relates to supervised learning, where your graph is associated, for instance, as I said, to a label or a scalar value, for instance, and you would like, in the end, to design an embedding space which is the most discriminant as possible, even if it doesn't preserve exactly all the graph structure informations. To address this problem, we try to use the optimal transport literature, and that's actually what we managed to do. And in a very broad sense, optimal transport is a very nice theory which provides divergences or distances to compare graphs or any kind of discrete probability measure. And it does prove to be quite efficient in many machine learning while operating whether on vector data or images by simply using so the very first paradigm of optimal transport, which comes down to operate within a common ambient space. And here in these phases, we mostly focus on the more recent paradigm, which comes down to consider transportation across incomparable spaces for which you don't have a direct distance to compare components in each respective space. And this optimal transport paradigm allows actually to compare graphs considered as spaces, while also providing correspondences between their nodes. It requires a slight modification of the formalism, where here a graph is now modeled as a discrete probability distribution, mu, where we have the support which is related to a tuple. So we operate over a project space of the structure, where you have the node xi, and the features denoted fi for every component of the graph. In the end, even with this formalism, the encoding is pretty much similar than the classical ones. You still have the connectivity matrix C, the feature matrix F. The only difference now is that you also have a probability vector H, which encodes the node's relative importance within your graph. In most cases, in real life scenario, you don't know anything on the node's relative importance. So the common assumption is to fix them as uniform. But afterwards, in this presentation, we will go further, for instance, by learning these representations, this relative importance. And for now, we still assume that everything is uniform until I say otherwise. Now that we model graphs as discrete probability distribution, the key tool from optimal transport across comparable spaces to really compare these objects relates to the Gromov-adjacent distance. So here we have two graphs which can have variable sizes, and informally the GWO problem reading as written here comes down to look for the minimal distortion of your input space while you want to transport it on the target space. So you aim at minimizing a kind of distortion of structure between both spaces. It comes down to this optimization problem where you look for transport matrix T, which satisfies mass conservation, meaning that all the mass assigned to the first space has to be same on the second one. And in the end, by looking at every pairs of nodes within each graph respectively and comparing them, An optimal transport matrix will aim at associating pairs of nodes that have similar pairwise relation in the structure of the first graph and the structure of the second one. You have an example on the bottom right where you match two graphs without attributes, which respectively have two communities. So minimizing the distortion when moving the first graph to the other comes down to find the optimal transport matrix, which assign one cluster of the first space to a cluster of the second one. So here you can hope to have small JW costs. In the end, it defines the distance, which is invariant to nodes permutation. And in an optimal transport context, an optimization context, this comes down to a non-convex quadratic program, whose solutions can be estimated using a conditional gradient algorithm, which is guaranteed to get local optimum with a complexity reading as follows, where, for instance, if you have two graphs which has the same size, will be cubic in the number of nodes for each iteration of your solver. Otherwise, if you're matching two graphs where for instance, the target one is considerably small compared to the first one, you may consider that your complexity is quadratic in the number of nodes of the first graph. Then, as in most scenarios, we also have features on the nodes of the graph. The fused Gromov-Weierstein distance kicks in, basically generalize the JDBG distance that operates only on attributed graphs to attributed ones, and it does so by considering a trade-off between the distortion that comes from the JW cost applied on the structures and a Wasserstein cost applied directly on the features. It will be actually a weighted mean parameterized by the parameter alpha, which weights the importance between the structures and the features. And in the end, the optimal transport will now associate pairs of nodes that have similar pairwise relations with respect to the structures, but also similar features. It also defines a distance, and in the end, the optimization problem that relates to the FJW distance is also not convex, and the iteration for solving them have most likely the same complexity. So now we have everything to go into the contribution of the thesis, which basically aim at mixing both worlds, graph representation learning and optimal transport. The very first paradigm relates more to unsupervised learning and is called graph dictionary learning, and basically aims at extending a key tool for unsupervised representation learning on vector data, which is dictionary learning, but this time to graph dataset analysis. A very first contribution called online GDL we'll use the JW distance to define a linear model over graphs, so that we end up with a linear dictionary. And also, what was quite interesting with this contribution is that it allowed to highlight the importance associated also to the nodes relative importance within a wide learning representation. And that's why it motivated our second contribution, which was semi-relaxed JW, which is basically a relaxation of the original transport problem, and also naturally provides a dictionary learning algorithm. Then the second section will deal with mostly supervised learning for graphs, and we will try to establish a first link between optimal transport on graphs and also the flourishing literature of JNN for end-to-end graph representation learning, where they are known to be able to predict really discriminant node embeddings, while optimal transport on graphs allows to take into account global properties of the graph. So let me begin with graph dictionary learning. So here we go back to our representation as embedding a graph within an embedding space, except that here, what we will aim for is to learn embeddings of the graph, which are associated to an embedded graph. So you preserve a graph representation while you're doing this embedding step, and you want it to preserve the best as possible, in a certain sense, properties of your input structures. To this end, what we propose is a first linear dictionary approach, where we will learn graph templates, and it particularly denotes from the existing literature, which provided a non-linear model based on JW barycenters. So To put it more formally here, let's say that we consider a graph without features for now, and we aim at approximating it using a weighted mean of target structures, denoted here as C bar K, highlighted in blue. And for this sum to make sense, actually, we enforce all the structures to have the same size. So in the end, in the embedding, all the graph will have the same size. Moreover, for the sake of interpretability, we constrain the embedding here, WK associated to one graph, to belong to the probability simplex, so that, for instance, if your input is a binary adjacency matrix and that you have atoms which have continuous entries between 0 and 1, this weighted sum will actually have values between 0 and 1, and we provide, instead of a kind of binary connection, more something now as that can be interpreted as the probability of connection between nodes. So to illustrate all this learning paradigm here, we aim at minimizing the GDB distance from the input to its model, which is a weighted mean of structure atoms. And for now, we assume that we know all these structures. So in the end, it just comes down to project any observed graph sample on the span of your dictionary in the GDB sets. You have an example on the top, where we consider on the right a graph sample with two communities and, let's say, small graph atoms, which are considerably smaller than the input. And here, these atoms represent respectively a small graph with 3 communities, another one with 2, and the final one with only 1 community. By solving this embedding problem, what you expect is that you have a weight on embedding, W2, which is the highest, so the closest to 1, meaning the closest to the extremity of your simplex that is associated to the graph atom with only 2 communities. And if you, for instance, add connections between the 2 communities in your input, what you expect is to have a linear interpolation between your small graph atom with 2 communities toward the one with only 1 community. So you will have the red dot in the middle of the edges corresponding to the 2 atoms. To look more into details with respect to the optimization problem here, so it's sure that when you say we aim at minimizing the GDB distance between an input and a model, within it, there is an optimal transport problem. So here, our problem depends on the embedding W that we want to learn, plus the matching coming from the optimal transport matrix. And to solve this problem, we suggest to do a block coordinate descent, where we optimize alternatively the transport matrix, followed by the embedding problem. And both are estimated in our contribution using conditional gradient solvers. What is nice with this linear model is that actually it provides a proxy to GW in the embedding space, meaning that let's say that we have 2 input graphs, C1 and C2. We embed them onto our dictionary, and we get these 2 representations, weighted means of structure matrices, weighted respectively by W1 and W2. These are still graphs, so our assumption is that a good way to compare them is to use GW. So that's why it's interesting to have this upper bound, which basically tells you that you can approximate the GW distance between the models simply using a malalignable distance, which operates on the embedding WE. So there's the expression of the PhD matrix here, which basically depends only on the structures of each graph atoms. Okay, for now, I still assume that we knew the graph atoms, but in practice, what you want to do is to infer them from the dataset composed of several graphs. And this comes down to this optimization problem here, where you will simultaneously look at how to represent the best as possible every graph of your dataset onto your model, and to also find the structures of the graph atoms that best correspond to your input. So it reads as this optimization problem here that we propose to solve using a stochastic gradient algorithm, which is mostly inspired by what was done for dictionary learning on vector data. And it comes down to the simple algorithm where it iterates over sampling a batch of graphs from the dataset, solving each embedding problem independently, so that you end up with every embedding and transport matrix linking the input to its model, so that you can finally perform a gradient step to update the graph structures of your templates. So a projection here is introduced just to say that, okay, for instance, if we have a priori knowledge over our inputs, like adjacency matrices, so they could be like, that could be wise to just help the learning problem by constraining your graph structures to be positive, or I mean non-negative in this sense. In the end, when you look at this solver, the complexity for one epoch is considered as being only quadratic in the number of the maximum number of nodes within your dataset. As in the end, we are in a factorization context here, so we try to learn very small atoms compared to the biggest graph of the dataset. So with all this explanation, just to give you some examples now, let's say that we have a dataset that is composed of many graphs generated by stochastic block models, whether with 1, 2, and 3 blocks. So they have different sizes, different parameters within their respective stochastic block models. And in the end, when you learn a dictionary using only 3 atoms with 6 nodes, you end up with the learner atoms that I showed you before in my examples, which are respectively a small graph with 1 cluster, the other with 2, and the final one with 3. And if you look at the embedding space, so the embedding WE, you can represent them in this probability simplex. And you see that if you consider that every number of clusters is associated to a class, so you have 3 classes, and you see that here you can perform easily clustering just by looking at the embeddings of each graph. One thing which is interesting from our model is that in the end, if you achieve, if you manage to reconstruct well your input using your models, so having in average a small GW reconstruction, what you end up with is that the Mahalanobis distance over the embedding is highly correlated to the GW distance between the input graphs directly, even if the Mahalanobis distance was between models. So here on this illustration on the bottom right, you have a Pearson correlation coefficient of 0.96. So that's why it's a good approximation. However, this model also helped us to identify some limitation of our model. Basically, let's look at the example on the top. So here you have a graph coming from a real-world dataset composed of social networks. And in social networks, what often happens is that you have hubs, meaning that you have people that interact with everyone. So they are, let's say, the most famous ones. And you don't want, when you represent this graph, to lose this information, which can be quite important. And what you have on the right is actually the model that you learn by learning a dictionary over this data set. And this is the representation that you end up with, assuming that all distributions over the nodes are uniform, whether for the model or the input. You see that in the end, you lose the central node, so that's not what you wanted. And this is mostly due by 2 reasons. The first one being that in our model, we fix the resolution of our graph atoms to be shared. So when you have a dataset composed of very different sizes, that can cause this problem of resolution in the embedding. But also one thing that we observe is that the learner representation using our dictionary are quite sensitive to the choice of distributions over the nodes, which advocated to learn them actually. And that's why we focused next on leveraging this last degree of freedom provided by optimal transport by attacking directly the mass conservation constraint inherent in FGW to get more flexibility. It led to defining the semi-relaxed GW divergence, which is this optimization problem here, where you will learn also in the matching, so your transport matrix, and also like the target distribution of your graph structure. So in the end, it comes down to match 2 graphs while reweighting the nodes of the target graph, so that you end up with a target graph at minimal GW distance from your input. On the top, you can find some examples where we color the nodes of every time the graph which are on the left of the matching, depending on the clusters that the nodes belong to. So here we are matching, for the first example on the left, a graph with 2 communities to another graph with 3 communities. And we see that the transport matrix, when solving the GW problem, while fixing uniform weights on the nodes for both graphs, will send each cluster on the 3 clusters while dividing the center in the middle of the target structure in 2, meaning that the target structure has to be highly distorted to match the input 1, so that you end up with a high GW cost. And then when you will start to learn the distribution on the target structure, what you see is that you will put the mass assigned to the third cluster in your target structure to 0, so that you can isolate in the target domain only 2 a graph with 2 communities, which will be the closest as possible from the input, which also had 2 communities. And the final matching on the right is just to highlight that while computing, this divergence is asymmetric, meaning that we only learn the target distribution and not the input 1. So if you reverse the matching problem, saying you match a graph with 3 communities to the one with 2, what you will do is to delete some nodes within the communities of the target structure, so that you end up highlighting a graph with a subgraph with 3 communities. In the end, this problem might seem difficult to solve, as you have a nested minimization over the constraint of the transport problem of GW, but it is actually equivalent to solve this minimization problem on the bottom, where you only have now only one constraint over the rows of your transport matrix, which essentially makes the learning problem easier in the sense that now the transport matrix has its rows which are independent between each other. And then we propose also to solve this problem using a conditional gradient solver that is about the same complexity of the GW problem 1, but actually that has some nice properties too, as it goes faster and scales nice on GPUs. And one example that is nice to give you some intuition on this matching problem now is that we looked at only one graph, a quite structured one, saying that, okay, we create a graph using the stochastic block model with 3 communities and with variable proportions. And let's say that we want to do graph partitioning, meaning recovering the communities of the input graph just by doing a GW matching. To this end, what we do is that we consider a diagonal structure as target domain, and for simplicity, we stick to the identity matrix. And for the beginning, on the illustration on the left, we assume that this target structure has uniform weight. So when you do this matching here, you see that the biggest community has too much global mass, total mass, to be sent on only one node of the target domain. So you see that the node in the center will have to aggregate mass from the big community and the smallest one. So you end up with a bad partitioning, quantified here by adjusted mutual information. And also, you are sensitive to the number of nodes that you put on the target domain. So if you say that, okay, I don't know the true number of communities in my input, I look at the matching to an identity matrix with 4 nodes. The 4th node has uniform mass that has to be completed. So mass will be sent from the input to this node, which will also correct the graph partitioning provided by the transport matrix. And everything changes actually when you look at the matching on the right, where now we look at the semi-wax GW divergence from the input to the target domain, where you will see that actually the masses associated to the target domain now are proportional to the proportion of the communities within the input. So you end up here with a perfect partitioning, which in the end, if you also missed the true number of clusters when doing this matching, let's say that you assume that you had 4 nodes in the target domain, computing the semi-wax divergence from the input to this graph, we just put 0 mass onto the 4th node. So in the end, you will have a perfect partitioning, plus you will recover the true number of clusters when doing this task. Overall, we show that benchmarking this on real dataset, the semi-relaxed GW divergence competes with unsupervised state-of-the-art methods dedicated to graph partitioning while being more generic. And from there, we also look into performing dictionary learning, in the sense that now we have a full data set of graphs composed of many graphs with variable structures, and we say that, okay, we will learn a unique target structure by minimizing on average the semi-like GWU divergence from the input to this target structure. It basically can be understood as a very center problem using the semi-like GWU divergence. What is nice is that now if you look at every single matching, considering the second marginal of each transport plan actually gives you an embedding where you will have now every embedded graphs, which will be related subgraphs of the single atom structure C bar. So this problem can be solved exactly like GDL, except that the embedding step, computing the weights associated to each input, is just now a byproduct of solving a unique transportation problem. So this is much less complicated, and the complexity overall, and it's much more efficient actually. So some experiments of this Berry Center problem. Here we considered also a dataset composed of social networks. So communities usually with hubs, etc. And we learn a dictionary of size 10, which is illustrated on the right. When you look at it, you have to consider every subgraph that it can produce. And we assign colors to every node of this dictionary. And just by computing the semi-like GWU from the input to the dictionary, you highlight the third graph, on the third column graph, where you only have 4 nodes, where every proportion of the node, actually, the mass associated to them, corresponds to communities in the first graph. So for instance, if you look at the biggest yellow dot, it will be associated by the transport plan to the biggest community in your input, which is also colored in yellow here. And what is the most important is that we also recover the central node that we were aiming for. So you have a more complicated example on the bottom, but the idea is the same. And one thing which is worth denoting is that when you increase also the dictionary size, you can improve the resolution of your embedded graphs. So what happens when you, for instance, you want to perform clustering of your dataset of graphs when you learn your embeddings using these dictionary learning methods? So here we simply did a benchmark on real dataset using K-means algorithm on embeddings, whether using the Euclidean distance for semi-like GW or the dedicated Mahalanobis distance for GDL. And we compared our algorithm to the first one being JWK, which is a kernel algorithm, K-means algorithm directly using the JW distance over inputs. And another competing method is JWF, which is the Berry Center-based dictionary learning approach. And in the end, we saw that our two methods outperforms consistently like these competitors across all data sets. And one thing worth noting also is that the semi-like JW dictionary learning is actually 100 times faster approximately than JDL and base competitors. And one thing which is quite interesting in the end is that we observed a beneficial denoising effect, meaning that actually, so you can cluster graphs using the embeddings, but by essence, we aimed at preserving embedded graphs. So a graph structure, and the good way to compare them is still using the JW distance, for instance. So we showed that, for instance, if you perform spectral clustering on your embedded graph or SVM in a classification context, you considerably increase the performances of the equivalent algorithm, which is directly applied on the input. So you have that's why you have this beneficial denoising effect. Okay, so now change of paradigm. We focused on supervised learning and try to establish this first link between optimal transport on graphs and graph network relates to message pacing neural networks, which are actually a kind of generalization of convolutional neural network that were operating well on images, but now we focus on graphs. So the idea is that for convolution, you look at a grid centered over each pixel. Now you will look at the adjacent node centered at a given node. And you will refine the node embedding of a given node by aggregating information iteratively of the features of its neighbors. In the end, what you end up with using this kind of GNN is a refinement of node features while taking implicitly into account the graph structure through this convolution mechanism. So you have node embeddings coming from this process, and to achieve graph level tasks, you need a way to aggregate them within a single vector embedding that can be read, for instance, by a classifier at the top of your architecture. And this step actually relates to a pooling, which takes into account all node embeddings. And the big question now is how to pool. The thing is, you have all these node embeddings coming from every layer and every node of your graph, which can be seen as distributions. So one thing which is simpler to do is to say, I will compute the mean as a pooling. And so this is efficient in practice to compute. The thing is, you don't include necessarily the more information regarding the structure of your graph. You just hope that your process to create node embeddings understood it completely. In the end, what we proposed was to try to find a way to take into account globally or fully these full distributions by computing their distances to some templates. One thing which we also propose is to use actually the FJW distance so that you can include explicitly by computing these distances the structure of your graph in the embedding. So this way, if you provide also explicitly the structure within the embedding, you may hope that the preprocessing of the node features will have more room to, and will have more room to just promote discriminate node embeddings. So this comes down to this full architecture here, where you have your input modeled in an optimal transport context. You preprocess all the node features using a GNN, denoted here phi-u. So at the output of this GNN, we still consider that we have a graph with the same structure and just change node features, and we compute the FJW distance from this input to graph templates. So these templates will be learned, and in the end, what they provide is a vector of distances, which will be read by, for instance, a nonlinear MLP to predict a label. So in the end, what you will do is to optimize a cross-entropy loss, for instance, considering the true label compared to this predicted label, and by backpropagation, you will update the parameters of your MLP, followed by the graph templates, and finally the parameters of the GNN. One thing which is interesting to note here is that we also learn the parameter alpha involved in the FJW distance, so that we have also a flexibility over the importance between the structures that we provide explicitly to the embedding and the features that the GNN is producing. So here, intuitively, as we are using the FJW distance, which is 0 if graphs the two match graph are isomorphic, you may expect that you have high expressivity in your model, meaning that you have high ability to distinguish graph between them. This, in the general literature, these expressivity notions are related to what we call Westphal-Lehmann isomorphism tests, which are practical because you can distinguish many graphs just in linear term regarding the number of nodes. And so this relates to a complexity 1 if you're on linear. If you increase the complexity of your test, you have a numerical complexity, which also grows exponentially with the complexity of the test. And basically, just as a sanity check, we just considered our model, TFGW, without GNN preprocessing. So we just learn the graph templates and read the distances using a MLP over 2 datasets for which we knew that the Westphal-Lehmann test fails. And that's what is summarized in the table here that you can find. It's just the classification performances over these two datasets, where you can see that, for instance, the model which are as expressive as 1WL fails. Another model which is more complex and cubic complexity is PPGN, which tries to tackle well this problem, but fails on the second dataset, which is more difficult. And in the end, the TF-GW model that we introduced performs well on both tasks, so we could assume that empirically the expressivity is better. So now we look at what happens when you consider the real datasets. So we compared many methods based whether on GNN, kernels, and the takeaway message here is that when you use TF-GW with a well-known automatic process, denoted here GIN, which is quite simple to implement, is that you improve dramatically the performances on these kinds of datasets, across all datasets actually. One final thing to note also is that as we let a bit everything free, if you look at the distance embeddings while using projected PCA, for instance, you will see that you have your point clouds associated to each samples of your datasets, and you also have the graph templates, which defines an envelope around these point clouds. And in the end, if you look at their representations, their graph representation, as they are very far from the point cloud, they are actually exaggerated versions of your graph samples. So if you look at the samples on the bottom, you see that your templates are quite not similar. And you can also see that in the end, if you introduce the GNN preprocessing or even more templates within your embedding, you will have this envelope which will grow and which will make the templates even less interpretable and your point clouds even more linearly separable. So to conclude on the contributions, FGW was introduced to design a structure-aware global plugin for graph-level GNN and showed many interesting properties, whether in terms of expressivity and generalization. Our reflection regarding graph dictionary learning allowed to change of paradigm from the graph isomorphism notion coming from GW to the sub-graph isomorphism problem using our relaxation. And this GDL algorithm showcased many benefits for whether graph partitioning, clustering, classification, also something that I didn't show were compilation that we look into, or online subspace tracking. And note that all these methods are implemented so free to access on Python optimal transport package. And they also let us envision many perspectives for work, meaning that for instance, we could consider very structure-aware or distance-based pooling in the sense that it increases clearly the generalization abilities of the model, but it has a cost. So it is limited to certain kind of datasets with not too big graphs, and we may look for better trade-offs. We could also think to couple the nice property of GNN to produce discriminant embeddings with actually our dictionary learning method, which doesn't apply any preprocessing on the node features. And this can be interesting to design new unsupervised or supervised graph machine learning models. There are also many links to establish with the graph literature, whether between GW or its semi-relaxed version that can be related to estimation of well-known graph random models, graph coarsening, etc. We can also think about designing novel generative models, whether by considering what is called graphon, which relate to graph limits and for which recent relation has been established between GW and estimators for these graphons, and we can look further into also defining novel mixture models. And one thing which is sure is that there are well-known issues related to robustness of these balanced transport problems and many complex challenges regarding their optimization. So a lot of room for improvement that can be looked into the future. That's all. Thank you for your attention, and feel free to ask questions.
Thanks a lot, Cedric, especially for the timing. Actually, you also say 1 minute, which
Yeah.
So I think it's time to pose the question of mostly and primarily from the viewers. So you can start maybe
Yeah.
for us.
Do you want me to switch from?
No,
Yeah, sorry.
Also the questions from the viewer, and you can do your best for addressing questions. So I suggest to start with the viewers and then to involve also people in the audience and myself, I'm curious. Go ahead.
Ja, zoals Gabriel Cansa, peut-être
Your answer. What you are planning?
Okay. So I can start if you want.
Yeah, go ahead.
Okay, so maybe first a few words about the presentation and the thesis in general. So I just want to say that I was very impressed by your manuscript first, and I think your presentation is in the same direction. It's really brilliant, very nice illustration, and the results are superb, so very impressive results on very timely questions about graph neural networks, which is very odd. And despite this, you're able to make contributions. So I think it was the first time that I'm really like optimal transport works. I mean, it's for some tasks, and it's quite nice for me, which I'm more a theoretician, so I enjoy a lot. And I see that theory and the practice comes together in such a beautiful way. So, okay, congratulations. So maybe now I start with the congratulations. A few questions. Maybe one thing I like to start with is, from what I understood, in most of your work on graphs, you directly use basically the adjacency matrix. So for instance, when you do global assessment computation and stuff like this, you directly input the adjacency matrix, which in my view is a bit problematic, I would say, because I think somehow you like to use more advanced geometric objects, such as the geometric distance, which you mentioned at some point, and I had a lot of discussion with really the whole time about this. I mean, I don't think we can to conclusion. So I'd like to have your opinion about adding like a first layer that basically map toward like using distances. And maybe a second question is, do you have learned this layer? Does it make sense?
Yeah, thank you. So yeah, in practice, in most cases, we use the adjacency matrices as input representation for the structures. One sanity check that was done before doing so actually was to see that in practice, contrary to the experiment that were done for instance, the JW or FJW kernels using SVM, for instance, on graphs, adjacency matrices seem to perform better than shortest path matrices to distinguish graphs. So that was the first prior consideration. And it's true that it was quite well appreciated that to see a contribution from Chaudhary that extended this assumption from over using GW between metric measure spaces to any kind of measurable spaces. And it's true that we also considered like over representations depending on the task. So for instance, for graph partitioning, there's it kernels which were proposed, so derived from Laplacian matrices, which seem to actually perform much better than adjacency matrices for graph partitioning tasks. So you have an inherent denoising effect over the structures, which seems relevant that we didn't consider in the GNN model, for instance. We just stick to adjacency matrices, but it can be something to look into. Clearly, I believe so. And using, I mean, the short, the shortest path distance is a bit more tricky in the sense. Well, we did experiments on our GNN model where we considered as input the shortest path distances, but still using, so the first observations were that it was more efficient if you didn't introduce any GNN proprocessing. than adjacency matrices. On average, across the sets, we had better performances. But when we introduced GNN preprocessing over the node features, adjacency matrices became more, better in terms of generalizations across all data sets, mostly. And so in a way, we believe that a GNN can actually encode this notion of distances between nodes, which are provided by the Schwartz path distance, and the adjacency matrix is enough. Plus, it's something that I didn't look into, but it seems more adequate to use when you're also using a GNN preprocessing, which use a notion of adjacency just by looking at neighbor nodes. So it's also an open question to say maybe propagation systems within GNN should be matched with this input structure that we are using in the FJW models. It's just something I didn't look into. Yeah. I hope it answers your question, even if it's a really broad, broad discussion.
I don't know if there is really a good answer, but
yeah.
Usually I would say, if you don't look at the other layer, like just inputting adjacency is too local. Inputting genetic distance is probably too global, but I guess it could be like some way to learn this, learn the correct scale if you want to analyze the graph. But okay, maybe because of the other layers in the networks, it doesn't matter so much, so we need to answer in the pipeline. But quite convinced. I agree that the necessity matrix defined in the space, it's a very detailed space. So I think it works not because of theoretical paper or the same or the sometimes, and you can work with the estimated space because you could have a very bad metric representation. So okay, I'm still puzzled.
Yeah.
I understand that. In practice, it both works, so it's probably good also. Maybe another question is about like the second part of dictionary or the second part. I'm wondering if you are, because in the good old days, like maybe 10 or 20 years ago, it was very fashionable to do linear dictionary learning, not with, of course, software. And at the time, there was very few mathematicians that still did this problem, but I think like maybe Mobile, for instance, we had some theorems about like, can you really programmably learn a dictionary? Do you think it would be possible to have some theoretical result or at least some theoretical result that say that the algorithm you propose learn the correct dictionary, generative model for your data coming from the dictionary? Do you think your algorithm could recover it, and do you think it could be a way to prove it? And what is the insight about what are the type of models algorithms can recover?
Yeah. No, it's like for me, in a sense, it's related to the notion of overcomplete dictionaries. But maybe I won't go directly through this. In the sense that the intuition that I have is that the first model, which was using dictionaries, computing dictionaries using JW barycenters, is actually more natural in a sense, as it will follow geodesics in your space. So you could assume that a graph that is over this geodesic is a relevant graph, and in the end we can see our approximation, our linear model, as a kind of linear approximations of this manifold that should actually be followed by barycenters. So in the end, impossibility theorem for our model to represent all graphs, I'm not sure. Well, maybe the question, I don't know, it's complicated to answer this, but there's also, so one first thing that we didn't look into is that from our dictionary, can we estimate well all the, really have bounds on the reconstruction between the GW distance between inputs. So we don't have bounds on these theoretical results which show that JWF is better than GDL, for instance. So non-linear versus linear is better. I think there is also like this notion of actually input representation, which is nested behind it, in the sense that even if you fix the resolution as we are doing in our linear dictionary, we may end up with representations. I mean, we may end up with zero reconstruction for, perfect reconstruction for all our inputs, even if we fix the size in the dictionary, just thanks to this notion of weak isomorphisms that comes from operating on adjacency matrices, for instance, and so on. Yeah, I'm not sure I answer, but like it's rather tricky in a sense.
Maybe a last question. I don't want to speak too much. Several questions. Maybe I will pick one on the list. Yes, so maybe one question about like the overall structure of your research. There is basically two first last one on pooling and one more like dictionary learning. And it's like almost disjoint, but I think it would make sense to try to fuse them together like a single architecture, which we use basically dictionary learning and weight computation as a layer, instead of doing like processing, you like fuse everything. Would it be possible? Does it make sense? And do you think it's interesting to have like a layer, which is like a variational layer, and optimize weights, as people try to do nowadays in the really works?
Yeah, I agree with this. So one thing which is also related to, so it's actually already done to do autoencoders using JW embeddings in a sense. Meaning that it's mostly for now related to this notion of we can estimate a graphon from estimating a barycenters using JW, and a graphon is basically something that from which you can sample to generate graphs of any size. So that's something that was studied to do autoencoders, basically variational autoencoders. The thing is, what happens when you learn a dictionary, in my opinion, is that you end up with defining a manifold of graphons, where you have your embedding weight, W, as I denoted, that allows you to travel across this kind of space of graphons, in a sense. So you may still perform this sampling strategy, even from your dictionary embedding. Or you could also even think about something maybe less generative, but more like end-to-end for supervised learning, which is quite inspired by what was done on dictionary learning beforehand, using, including directly the weights involved in your dictionary within a classifier, and minimizing both classification error and reconstruction error, finding a trade-off between both. So I think these are two ways to potentially see the problem. And so you have the aspect coming from generative models by sampling using this kind of graphon theory, I believe. And also trying directly to use actually the weight W to perform classification. And it's not something that I really looked into for now. But I believe that it can be quite relevant, and it can also become even more relevant while using the semi-relaxed JW, as in my opinion, it has more degrees of freedom as it provides a divergence between structures, but also an embedding just by computing a single transport plan. So you could learn from both, and well, still something that I hope I will have time to look into soon.
Okay, so thanks for the insights and discussion. So I leave the floor to the other. I have a lot of questions. It's time for me to give the floor. Congratulations once again for your very nice work and your very nice presentation.
Thank you. Oui, I can hear you.
Okay, so first of all, yes, I would like to congratulate you. So your PhD is not only very interesting, but it's really making links between words which are not always, or for a long time, which are not been linked, so it's interesting. And of course, talking about optimal transport, structured data, and GNN. So you touch many topics relying on dictionary learning, HuffConnect, and also relatively strong background in optimal transport. So congratulations for that. Your PhD thesis was very interesting. Sometimes a bit elliptic for me. I wish a bit more details on some parts, but very dense and impressive work. Very nice publication. So for your presentation, you chose a nice way to present things, and I'm going to follow the line of this presentation. First of all, I would like to ask you, so on dictionary learning, the fact that you choose the linear expression instead of the filter one, does it mean that if you want to extend the method on the oriented graph, you may encounter a problem because we previously in the discussion recall that Goma can be indeed extended to not only to ground metrics but
Thank you for your comments. Really appreciate it. In the end, it's just, the main motivation behind what we focused GDL, the paper, on undirected graphs, was that it was difficult to find datasets of directed graphs. And yeah, for real. And also that at this time we hadn't really included these notions coming from the extension of GWU, the theoretical notion from GWU of over metric spaces to any kind of spaces. But actually, I don't see many reasons for the model to fail, except that in this scenario, if you have inputs which are directed, you don't enforce the atoms to be directed to. You let them being asymmetric if they need to. Plus, actually the bound, for instance, the Mahalanobis distance is still true. It's just like there's a transpose in additional one. It's true that I didn't put this in my manuscript, but it's, from the proofs, it's really simple to see. And I also tried to, also in the paper, we discussed the notion of computing gradients to learn target distributions, for instance. And at first in the paper, it was so focusing on undirected graphs, but a simple extensions coming from a change in, a missing factorization that you can do when you compute gradients of GW over directed graphs or undirected graphs. Just provides actually a rather analog algorithm, subgradients, sorry. So no, I don't think that anything changed, and that was more for practical reasons actually.
Okay. In practice, I can tell you that it works a bit less. Because of the difficulty of the problem. Because of the difficulty of the problem in the sense that the oriented graphs were much more possibility than the complexity of the problem. But yes, it's a nice answer. I want to come to the semi-relaxed divergence biology divergence. And I want to ask you, so you really nicely show how this divergence relaxing on some side the for instance, to be applied on the main problem where you are going to relax the association on the target. So you show a graph condition, you show a graph partition, and it's very nice. I found it very original and very elegant. But I want to ask you if you are interested to take benefit from this luminous divergence in problem where you would like to have really a distance or say symmetric processing both sides. Did you look at aggregating the results of two divergence on the left side, if I can say, divergence on the right side, and so you two kinds of problem and elaborating at the end, or something like that. Did you try something like that?
Yeah. Actually, like, I mean, I had a lot of hopes for the Simulax GW trying to prove stuff. I basically wanted to check whether it was defining a quasi-metric from which you could really hope to end up with a metric when you consider a symmetrization. But I provided some complementary results in my manuscripts, which say that maybe it's just wrong. But yeah, to answer your question more directly, I considered also like the symmetrization of the problem. Well, in practice, I just tested that whether it was useful to define a kernel, for instance, that was more discriminant than simply applying GW or something. And it wasn't that convincing in the end. It's hard to say whether it comes from the fact that potentially the Simulax GW also suffers from higher approximation error than GW due to the relaxation, or just that you solve for each two optimization problem, so you increase their error at least by a factor 2, let's say. And then in practice, so it wasn't working that good, but anyway, it's still an open question how to well solve GW, hope for better solvers. The same goes for the Simulax GW. And more on the theoretical side, I do think that indeed it defines a metric actually when you look at the symmetrization of the problem. I do think that I didn't talk about it in my manuscript, but that I have somewhere the proof of the triangle inequality. The thing which is quite nice with this formulation is that what you may opt for having a matching which becomes invariant in the distribution that you assign to both graphs. As you alternate what you consider as a optimal distribution in the matching, and that's not something that I was able to prove yet, but I hope it's true in a way.
So now I would like to come to the nice work about combining GCM and distance-based representation mapping. And my first comment is I think something on which you did not insist on your PhD, but I think this is something that you could claim, so it's more remark than a question. So there is a bad echo. Is it normal or?
We still hear you properly. Sorry if
so really that, in machine learning, there is a continuum between dictionary-based approach and non-parametric approach. The only difference in non-parametric approach, basically, you can say that it's dictionary approaching, whereas the templates, the atoms, usually vocabulary, are data themselves. Okay? And you basically have to learn the weight of the data. So there's a nice link between that, and if you go further, the notion of templates and atoms disappear, you have parametric model. And so what I want to see, you did not push that a lot on your manuscript, but what you have done with representation based on prolonged distance in the last layer of your network, there is a parameter with the, let's say, last layer, which is the non-parametric model, where you have weights which are still to be learned. Like basically, your templates are directly the data. And I think that's similar to what Gabriel said. I think you work with game to be placed in a bigger, say, hybrid GNN networks from dictionary to non-parametric. Having said that,
Sorry, may I suggest to use the microphone when you don't talk?
sorry.
No, it's a great problem. It's opportune to mute the microphone.
Yes. Thank you, Mark.
No, that's a link, I think.
Is it better now? Yes, you can hear me as well?
No, it's not a problem on your side.
Yeah, I know. I think it's a good idea.
Okay.
Thank you for
Yes,
asking.
sorry for that.
Yeah.
Okay.
I thought there was something to add. Okay. Okay. So now I'd like to go back to the the training algorithm of your architecture. So maybe Cedric, you can put at least the architecture of your network. I think it's slide 24. Maybe.
I think I'm lagging a lot. That's nice.
Yeah, that's perfect. You can, sounds good, yeah. So, this kind of architecture is, okay, my first clue was that the way you use the graph complex is basically learn file, right?
I'm not sure. I didn't hear properly the question. Sorry.
Okay, so I'm just saying that you only use, I can say, your graph net to provide file queue. Am I?
Yeah, no embeddings. Yeah.
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 So did you compare this architecture with the idea of representing this new triplet of CI, FPU, of FI, HD, and distance? Did you try to look at, sorry, which is a little question. To me, it's a little bit, in fact, you only provide the embedding with your graph on net.
Yeah.
And you do that for the non-embedding. Okay. Surely, if you have more information, like information about the edges, you would do the same. You would easily include embedding of edges and edging.
Oh, it's not something that we looked into. The thing is for sure we need to get like in the end a connective matrix which each entry is a scalar. So we could consider also over JNN, which transform the structure matrix CI. Let's say that every edges are more than one dimensional. They are JNN that simultaneously encode node embeddings and edge embeddings. So that's something that we may look into, but we didn't yet. It's,
And so now, when you schedule your learning, okay, the training of this architecture, I can imagine that you have local minima, right?
sorry, it's a bit
So,
complicated.
You play with different conditions, and I don't take the minimum of all now, stuff like that, because I can't really be completely convinced that we don't fall in the minimized value level.
Well, anyway, we end up in a local optimum, I believe.
Sure.
For sure. It's true that it's actually quite costly to solve and to estimate all parameters of the model, etc. So it's trying to perform MC algorithm to enhance, for instance, the FGW matching at every iteration is an option, but it will clearly dramatically increase the computational cost, I think. And it opens clearly the way of, the question of do we figure the good initialization for this FGW matchings, which I believe for now is not the case. And regarding the full architecture, the only thing that I did in practice to make everything a bit coherent was to say that at first the templates, I sample them from the dataset. And so I have a fixed GNN. I pre-process the node features of my sample, and then I consider that it is a template. And I didn't consider any particular initialization at the end over the MLP, which may be also an option. And so yeah, in the end, the local optima that we end up with are rather cool already to get good performances in terms of generalization. It's something that is interesting also to consider, maybe to stop to do this kind of full end-to-end learning, starting right from the beginning, in the sense that at least we also showed that it was rather okay to fix, for instance, the template as samples, which relates to the backend theory. On some experiments, we had good results, even if they were not as good as when learning the graph template. So this could be used to perform like a kind of two-stage learning algorithm, in the sense that you fix the GNN, you fix the templates, you optimize the MLP at the end, and then you learn everything once again all together, starting with a good starting point everywhere. I wonder if it's better in some ways, even if it's improves the learning the learning process or fasten it at least. I don't know for this.
It's interesting to have a term where you have a number of authorized templates which increase, and if the constructive and incremental approach is worse or not. Anyway, we are in this local minima, so let's go for it. And I think that seems to do with it. Just the very last question. So, what is nice in the Grand Recherche that relying on ground metrics, for which you have relatively great flexibility, you can handle many problems for, let's say, graph representation and graph reflection and so on. And in the literature, there is other ways to deal with graph, and it's basically it's a kernel based on bag of substructure. Okay, so you use a bag of substructure. You represent your graph on this dictionary, and then you can go for linear or nonlinear. And the thing is, for some problems, this kernel finally, in some applications, achieve very good results because you choose, in fact, you cheat, I can say, you choose the best substructure, the best meaningful substructure. Okay, so you do some job, in fact, of graph representation is close. And my question is more general. So in Grand Recherche, you can rely on the ground matrix to define your optimal transport distance, but you didn't talk a lot about regularization, even though it's a little bit present at some point. But I wanted to ask you if you have considered regularization as a way of the mini regularization. If you can regularize the transport plan, you can solve the barometric problem with regularization of the weight. Okay, that's one. You can do some regularization on the barometric target itself. So have you considered regularization, or I would say maybe not regularization, maybe constraints on the graph? Have you considered ways knowledge, prior knowledge about your problem in this way?
So yeah, it's also a quite vast question. So in a sense, one thing that I observed is that it seemed for the graph representation learning task that we did to preserve in a way the sparsity of our transport matrices. The thing is, I benchmarked it at the time using projected gradient descent to estimate orthopically regularized GW problems, but it wasn't like working as well than the conditional gradient solvers. However, like there were a lot of new papers on the optimization of GW using this kind of alternative Bregman projection, etc. And I think it's hard to identify which solvers now, which relates to a kind of regularization, is the best actually for like across tasks in a sense, especially when you're doing graph representation learning. As for instance, with these solvers, what was observed is that you had errors on the feasibility regarding the marginals of your transport plan, and the fact is that if you know that your marginal is not satisfied, but you want to compute gradients with respect to distributions or masses in duration, I don't know what will be the effect Like it seems to me like a problem, but I didn't practice that much on them, experiment that much on them. So that is the first question. After also, like for the semi-large JW, within the matching, we consider several regularization, such as like solving by conditional gradient solvers, which solve exactly the problem using also a mirror descent using the Kullback-Leibler geometry, which now gives you an entropically regularized solver that doesn't solve exactly the problem. And we also try to promote sparsity over the marginals, the weights that we activate within the target domain. So these are three kinds of regularization which are relevant depending on the tasks. But I never truly considered having prior knowledge or additional constraints over, for instance, the graph structure, the graph atoms or stuff like that. It's true that I have issues to, I mean, it becomes, in my opinion, very task specific. I can't have like, I don't have a good idea of what could be quite relevant for graph representation learning in general. And well, maybe in a way, the thing is that when we observe the transport plans, for instance, in our graph representation learning framework, we see that essentially they are sparse. We often operate on graphs which are also sparse, which have like cluster-like structures or repeated motifs, like patterns, like triangles, cycles, if it comes down to molecules or proteins. And so all these things are recovered in a sense through your representation that you learn, and you have a nice association with these factored substructures. So you end up with a transport plan which is in a sense sparse. You may think from here that this is low rank, in the sense as you have also your representations which seem a bit low rank, as you have repeated motifs. But like the solvers that were used, that were for now introduced for low rank estimation of a Gromov distance, like I experimented on them, and it was not providing at all the same matchings that you may hope for using C conditional gradient and all. So maybe like providing prior knowledge with respect to this kind of notion of rank may be interesting, but it's a very open and hard question, I believe. And there is something, well, no, okay. So sorry, maybe I will stop here, but.
If you also have something, this is your PhD thesis. For me, I have finished, but if you want to add a point.
Yeah, I also think that, thank you. I also think that the linear model that we introduced for the graph dictionary learning approach, as an extension provided in the paper, we also learn a second dictionary over the masses, where you end up with two dictionaries. And I looked for a while into extending our Mahalanobis distance in our embedding for this model, where you have now a model over the structures and a model over the masses. And I figured new kinds of upper bounds of the GW problem, which involves weighted sum of transport matrices between graph atoms. So it induces a kind of dictionary of transport plan. No. So you have this kind of you may opt for this kind of like prior knowledge on ranks provided by your graph atoms, which maybe could be useful to fine-tune your inherent transport problem. But this is totally hypothetical. No. Thank you.
Thank you very much for your answer. Sorry to hear.
Okay, I think it's time for exam here. Laetitia, maybe you can, Laetitia?
Yes, sure. Thank you, Marco. And thank you, Cedric, for this night talk and this night manuscript as well. So I found that it was a really strong work with different types of contributions. So we have some methodological contributions, some algorithmic contributions as well, and we have plenty of experiments to validate what you have proposed, and also the implementation method. So I would like to congratulate you for all of this. And I have a few questions, and I have to say that they mostly relate to the ones of Florence. So I'm sorry, it's a little bit related. So I'm gonna start with a question about the templates that you considered. So it made me think about something that it is classically used when you want to do some learning and time series. So I don't know if you are aware of that, but you have something which is called shapelets that are kind of analog of what you have proposed, but in the case of time series. So in this case, the templates are parts of time series, and you at the end you end up with a vector that gives you the distance to several templates, to several shaplets. So as you propose, there are several ways to find those templates. And one classical is to plug all the process into a neural network, more or less as you did, and such that they aim at finding the best of the optimal shaplets to solve the task. And there is another alternative to do that. So either, as Florence mentioned, either you can take some data from your data set as templates, but also something that is classically done is to consider random templates. And in the community, they show that it works pretty well, and the main advantage of that is that it is computationally really interesting because you don't have to optimize in order to find those templates. So I wonder if you, what do you think about that? Do you think that it would be possible to take some random graphs? And what would be the impact of doing so? So in that case, you will have to take a lot of graphs, I guess, to have a good view of the space. So I don't know if you consider that option, or what do you think about that?
Thank you for your comments, Letitia. No, I didn't. I never saw anything like that, actually, like considering completely random templates to refer to for getting a representation. So that's why it's hard to tell you that whether it can be relevant for graphs or no. And in the end, in these models, do they learn along the way these templates, or like?
So yeah, you have several options. So one of them is to fully learn the templates and the weights as well. So just as you propose. But the other option is to take plenty of random templates and to try to optimize the weights, and at the end they have only few templates that are really relevant. But computationally, it's really interesting to do that because you try to optimize it.
Yeah, I see. Well, I don't know. In the sense that we already end up with templates which are totally abstract in a sense. So from the starting point, it seems difficult to even define the notion of random. Like it seems vast, and so I don't have really intuitions to provide on this for graph learning. No, well, no. I see the benefits that it can have. I also question like the benefits that can have like efficient sampling when doing applying background theory for graphs. I think that's an interesting question that can open like some good perspectives. But random, yeah, maybe. I don't know. It's also true that I mean, maybe to do a kind of parallel to the literature of graph neural network. So it doesn't relate directly to the notion of templates. It relates more on increasing the discriminability, I mean, the expressivity of a certain genome by simply performing augmentation of graphs, especially of features, by adding random features. And it showed that it actually, like, it is generalization, but it's not related directly to the notion of graph templates. And I wonder what happened if you I mean, does it remain relevant to do so when you are doing a TF-JW pooling? In my opinion, I would say no. But so yeah, that's about the only intuition that I have around randomness of the form. So.
Okay, thank you. So I was just wondering how sensitive is the method to the quality of the template that you can find. But that's
well.
I have also some questions related to your semi-relaxed version of Common Bassenstein, or Fuse Common Bassenstein. So I think that I understood why you have proceeded this way. So I have several questions. So the first one, which is a really technical question, is that at some point on your manuscript you say that you enforce the sparsity of the marginals that you have. So I wasn't really sure to see why this was a compulsory to do that. So first part of the question. And another open question is, do you think, so you build this semi-relaxed version, so I understand why, because it seems that it's more easy to compute, that's the full problem. So I was wondering if you have considered and thought about deriving a non-balanced or full unbalanced version of Grommel's Bassenstein, or if you have some ideas on that. And something that I was thinking of, so I don't know if you are aware of that, but there is one of a great paper of Yannick Chiza talking about semi-couplings. So I don't know if you are aware of that, but it's just these semi-relaxed things just made me thinking about that, saying that semi-couplings, so I don't know if you know, but you fix only one marginal and the other one is free. So I was wondering if we could at some point maybe combine the two semi-relaxed solution to have a fully unbalanced solution. Open question.
Well, sorry. So I guess definitely we have a kind of semi-coupling here, as we are relaxing both. In a sense, the semi-relaxed divergence is like an extreme scenario of unbalanced JW. But like, I think it relates also to the question of robustness, which will be the end goal of the use question, and that it's definitely sure. I mean, it's sure that with the semi-relaxed version we have issues regarding robustness, because in the end you end up also with preserving the mass from the input to the target, so you don't delete mass, and defining a kind of trade-off. For instance, using an unbalanced JW formulation. If now you go a bit further and instead of providing prior marginals from which you derive using the divergence in the unbalanced formulation, if you learn this kind of this target distribution, I think you can have a relation to establish with the semi-lax GW. But in which sense performing so gets you closer from approximating a GW distance between clean distribution is I think open, and that's some thought I had recently, and but I don't know the work of Shiza on the semi-coupling, so I don't see exactly like the direct connection. So for the last question, sorry I don't answer in the correct answer, and so the other thing was for graph representation using semi-lax GW was that in the end you may we didn't aim at learning really large target structure when performing semi-lax dictionary learning. So this is the size, in a sense, that for dictionary learning approach induces a high level of sparsity also, because you can consider that if you have a huge target structure, you compute a transport plan, you know that it has to be, if it's normally sparse, and you may think that at some point increasing the size becomes unnecessary, so you become in the setting of over-complete dictionary. So maybe I don't explain it clearly, but that was the notion. But here we focused on small target structure compared to the variability that we had in the input datasets, and that's why it was relevant to say, okay, now promote even further the sparsity of the marginals to compress even further the subgraphs that relate to every input. So you may contain even more information within an even smaller target structure. And in practice, it was performant to perform clustering. It also showed benefits to perform completion of graphs, starting from like considering that the dictionary captured the semantic of well-constructed graphs. You may help to reconstruct well partially observed graphs, and in this experiment, it was also relevant to compress the marginals even more. So this has a denoising effect, which relates to sparsity that we don't really control exactly when doing our dictionary learning approaches, which may differ from the conventional literature on dictionary learning for vector data. But that was the main motivation in a sense.
Okay, thank you. That's clear for me. So just to come back to what you said about robustness, so I understood that you define this generalized version to be some kind of robustness about that, but when you do sort of dictionary learning, did you study in of adding some spurious graph into your data set, and it would be beneficial to add some kind of unbalanced also on the way we select graph to enter in the computation of the dictionary learning?
I don't really understand unbalance in the way of selecting graphs, like unbalance over templates, over the embedding. You mean that it's maybe okay. That it's maybe not relevant to constrain them to belong to the probability simplex. That's what you mean in the end.
Yeah, I mean if you have plenty of wrong graphs in your data set, how is it published?
Well, it's in a sense it's robust because we use a condition. For instance, for GDL, we use a conditional gradient solvers constrained to the probability simplex, which end up providing a bit naturally like a sparse solutions over the n mixing. So, and when you promote sparsity over them, you discard non-relevant items. And we observed that in certain settings, when you, for instance, you just consider SBM, I mean, that set of SBM with different kind of blocks and proportion, etc. It's how to say, like for instance, for the task with with graphs with 3 communities at most, if you put too many graph atoms, it will just keep sending like embeddings, I mean, and mixings over a few amount of atoms, less than the total amount that you provided as a prior information, and it won't learn them in a sense. So yeah, it's a bit like a byproduct of performing exact solving over the probability simplex, and without this, I mean, yeah, I don't know. Otherwise, I don't see exactly how you perform. I mean, you could also impose a kind of robustness by directly taking inspiration from robust optimization. Let's say that you aim at optimizing your unmixings, and you had like a noise over them that defined a kind of ball with a bounded norm. You could look at minimizing the unmixing problem with respect to your unmixing, and while maximizing this norm. I mean this component that induces like a kind of ball around the unmixing that you select, and so that's something that was used to introduce a kind of robust GW matching recently, but it wasn't dedicated to the unmixing. It was like directly applying a kind of noise structure over the target structure when you're performing matching. It was relevant for robustness. They didn't address the question of doing the same thing over the masses, and neither doing this over the unmixing. So, like in practice, I don't have real insight whether it can work well or even if it's necessary. But,
Okay, thanks. I'm different.
Okay. I think his name was to Fontaine, you there, and another question.
Hi, could you hear me?
Yes.
Yeah.
Yeah. And thanks, and it's a very nice talk. And for your presentation, I think the logic flow is clear and the content is well organized.
Sorry, we cannot hear remotely.
yeah, okay, sorry. That's because I have to keep my microphone on.
Yes. Okay. Could you hear me now? Okay. So basically, I like your presentation, and it's easy to follow because the logic flow is clear and the content is well organized. And for your thesis, and I think it is self-content and systematic work, but I have 2 suggestions. Firstly is in the page 196. You cited my work. 2 of the papers are cited repeatedly, so maybe you need to double check your BIP file. And this is one suggestion.
Sorry.
And another thing is in the section of the semi-relaxed GW distance, and I suggest to add some visualization results for the transport planning you learned, because it's related to one question I will ask. And for your work, I have several questions. And firstly is for the GWL, you impose simplex constraint on the weights you want to learn. And I wonder whether it is necessary or not, because when I developed the GW factorization model, we have to impose the simplex constraint on the weights, because otherwise the GW layer system will be undefined. But in your case, you use a linear combination. I don't think that it has to be an average it can be something like a differential or something else. So what's the reason behind this design? Whether it has to be on the syntax?
Mostly like the reason was for the sake of interpretability, in the sense that well, it's nice to have your probability simplex to interpolate between extremities where you know a kind of structure. It's also helpful to have this interpretability aspect where, for instance, you want to perform online dictionary learning, and in this scenario, it might be interesting to provide prior knowledge over the graph atoms if you are expecting something from the stream, or there are many applications that relate to this. So mostly because it was what was working on. In a sense, there is a property which is rather inherent to solving the optimization problem with respect to the graph atoms, the graph structures. It was that if you learn over matrices which belong between 0 and 1, you end up with graph atoms which also belong to between 0 and 0 and 1. So it's true that it may be relevant to relax the weight W, consider that the constraints are sufficiently well posed over the graph atoms to get the quite good results.
Yeah.
It's not something that maybe it can be relevant in some.
Yeah, I think maybe it can be one of the future work, because in my opinion, maybe relax this constraint can improve the flexibility of the model. Because if the weight is negative, actually what you did is something like deleting some edges. And from the viewpoint of sparse coding or dictionary learning, maybe this constraint is unnecessary. This is my opinion and one question. And another thing is for the semi-relaxed GW, I think it is a kind of one-side constraint, the GW distance, right? So the question is, have you ever tried other algorithms like Bregman ADMN, because it can get a closed form solution at each subproblem? So did you try anything else like this, such as to compare the efficiency and the performance?
No, so like in the end, like we experimented with the Marwar descent using the cubical divergence. In the end, the updates are very similar than proximal point algorithm, where you do a unique update. I mean, sync on when, in a sense, in the spirit, I think it's similar. But I didn't try over algorithm to regularize in an entropic sense the semi-relaxed problem, and that clearly might be like relevant for the future too, especially in the sense that this kind of algorithm has still the very nice property of having every steps which are differentiable. So like that's also maybe a really interesting thing to think about if you want to go further on end-to-end models using semi-relaxed GDBQ, etc.
Yeah, the reason I asked this question is because I'm a little worried about the performance of conditional gradients in this case, because most of your algorithm is based on the conditional gradient. But in the semi-relaxed case, in some cases, I'm worried whether it will fall to some trivial solutions like these two extremely sparse node distributions at according low rank transport plans. This might not be a big deal for graph partitioning, but for subgraph matching, this might be a problem. So maybe you need to double check it.
No, it's true that with the conditional gradient algorithm, we just use like, I mean, the direction finding step is just closed form over each rows, and which actually don't have like unique solution if you have minimum which are located at a different position. So in practice, like maybe it was impacting my experiments, but I was in this scenario, I was setting everything to be equal, assigning the same same weight. So in the end, I guess it impacts the sparsity of the transport plan. And you're correct in the sense that there are some papers that look into graph partitioning, subgraph matching, etc. recently that highlighted that even for very good like shape matching in a sense, it's relevant to have this kind of smooth smooth transport plans. So it's true that we have good solutions coming from anthropic regularization. We maybe get. I do hope that we can have like better solutions using, for instance, a generalized conditional gradient solver, where you have like a regularized solver, anthropically regularized solver inherent to your direction finding step. But it's like just a very few experiments that I did quite fast, and it was working. But I don't have like theoretical grounding to support this. That's the global picture that I have regarding your questions.
Okay. So the last question is about the PFGW work, because in the end of your presentation, you mentioned that most of your work is focusing on the unsupervised and semi-supervised learning of the graph. So, but this model, I think, currently is in a supervised learning paradigm, right?
Yeah, totally. Yeah.
So, this is an open problem. Is it possible to extend this TFGW work to unsupervised learning? And do you have any ideas and whether it can be added in the conclusion section of your thesis?
Well, the thing is, like, you have for me, the transport plan is a kind of projection. So you may think that actually, like, with every method that we have, we are performing a kind of autoencoder with high structure imposed by marginal constraints. So I actually wonder whether it can. So that's why it makes difficult to see whether it will be relevant to go towards this kind of autoencoder in a GNN pipeline, saying we have an intermediate layer which is a TFGW, and can we generate graphs after that? I think there are there are good leads coming from graphons as a sense of performing variational autoencoders by means of FGW distances, which in a sense relates to TFGW. If you have this vector of embeddings towards, two different kind of templates, like a kind of mixture of graphs. Then, and also, it's also something quite hypothetical in the sense that if you go towards these questions of variational autoencoder based on FGW distances as embedding, there is something that made me curious in the graph limit literature, which is called GraphX, that I mentioned at the very end of my conclusion in my thesis manuscript. And it's interesting in the sense that what it questions is the sampling strategy of a graphon, basically. And it makes it a bit more realistic in the sense that it tries to introduce a sampling strategy which preserves more meaningful subgraph when you're sampling a graph at a given size. And it changes the formalism in a way that, for instance, to generate, so a GraphX is just a tuple of 3 components where you have the graphon, for which you still have the same sampling strategy over 2 points, and you say, let's say the graphon is W, you say W XCG provides you the probability of sampling according to a Bernoulli distribution, an edge. But then it adds what is called a star function, meaning that now suddenly from one point that you consider, actually this point is a star. is it's like you add nodes to your graph, and everyone is connected to it. And there is and its degree distribution follows the Poisson distribution according to a parameter of intensity. And there's a final step to, for instance, eliminate nodes which are isolated or stuff like that. And for me, what I saw looking at this, these are complicated papers on graph limits that needs clearly time, but it's, in my opinion, goes into the direction of establishing links between JW over graphs and Markov chains, which was something done recently to establish a first link between establishing a distance corresponding to Westphal element tests, which is actually a lower bound to JW over this kind of a Markov chain species. And well, maybe there is a kind of of bubble to pick here.
Okay, and thank you for your answers. And also, congratulations, and I enjoyed this talk.
You know what? I have a big question. I'm sorry, I did not hear you.
Sorry.
Okay. Well, thank you for the presentation and also for the work you've done with me. It brought me a lot, so it was really great to work with you. And so I wouldn't be so long. I just have a few questions regarding your works, and the first one maybe is regarding the partitioning experiments that you've done, and that shows in fact that partitioning according to the Gromov criterion is a very good idea and leads to very good results. So I think that behind there is something to grasp here, and maybe do you have any intuition on why this is true? This is a good idea to make the partitioning or the clustering of nodes according to the Gromov criterion.
Yeah, thank you, Titan, for your comments. And so, yeah, I mean, the very first link is like looking the big pictures. Let's say like the first link established on graphons, meaning that a barycenter, a JW barycenter is like a discrete approximation of a graphon. When you consider graph partitioning, maybe the first thing to look into is maybe not the first thing, but in the literature, something, let's say, not too complicated, is a stochastic block model. And it is actually like a piecewise graphon for which you may opt that a JW barycenter, where you estimate the structure and the masses, are actually exactly your stochastic block model parameters and so on. So this established, this still has to be proven, but intuitively it provides like a good starting point to think that graph partitioning can be really well done using JW barycenters where you estimate the mass, knowing that in this case scenario it's equivalent to learning a unique structure with semi-large JW for a unique graph, input graph. And then so we have the starting point, and going further is a bit delicate in the sense that it relates to a paper in process of review. No. And no, I'm kidding. And well, it's kind of hot topic. I don't know if I can talk. I can talk about it further, but no, yeah.
Not telling anything. And so maybe it's related to the question of Gabriel before that. Okay, so what you said is true when considering, for example, adjacency matrices, or is it still true for more complex metric or something like shortest path distances or?
For the stochastic algorithm block model, for instance, I'm not sure that it's no. I think it's true for the adjacency matrix, not for the others. I think that there are literature. I mean, quite inspired on stochastic block models and extension, like corrected degrees, stuff like that. That may come down to just consider. I mean, to get intuition, basically, you can look at the closed form solution of SR-GW barycenter, and maybe see if it's relevant regarding to your initial problem. For adjacency matrices, I believe that it is quite relevant for stochastic block models. You can hope to get over a parametric model from one number graph, like not corrected degree, using normalized adjacency. So, well, I just checked at this quickly using the equations, but I don't know if we can have. One thing which is quite interesting also is like many people in this kind of literature, graph partitioning and coarsening and so on, so tend to look at matrices derived from the Laplacian matrix, which is a PhD matrix. So if you learn a barycenter, SR-GW barycenter with this kind of input, you know that any substructure that will be activated with positive masses, also PhD, positive symmetry matrix. So you may hope that you have a nice, the barycenters has a nice meaning information regarding to your input. But defining exactly what is this meaning depending on the input is an open question that I don't know yet how to answer. But I will look into it.
Okay. Maybe a second question. I was thinking actually on the question about could it be like extended to unsupervised cases? Like for example, if we think about the template-based model, it would be nice to have something that works also in the unsupervised case. And I was wondering if it would make sense to consider some contrastive learning algorithm. I don't know if you're familiar with it, but the idea is to learn mostly semi-supervisedly or unsupervisedly, something by adding noise. For example, we could learn something by discriminating noisy graphs from not noisy graph, and learning this way some template-based model as you've done. Would it make sense, do you think, or would it be possible?
So I don't really know if in the end it will be that useful, in the sense that so we introduce the TF-GW pooling layer, knowing that it has nice benefits as it takes into account explicitly the structure in the embedding, and we did also consider that previous to this paper, a Wasserstein-based pooling layer was already introduced. So that now, just instead of computing FGW distances to a template, you just consider the point cloud of knob embeddings that computes its distances to a point cloud template, several ones. And so we did experiment with that. And the authors mostly studied the task of regression. And they also introduced this kind of contrastive learning, actually, in their paper. I mean, the results were a bit mitigated. They were tackling regression, so they basically considered more templates than I did for the experiment in classification. And I never observed any kind of collapsing where you were learning a small amount of templates, well initialized using input samples, and also learning the masses of your templates. I feel like this degree of freedom allows you to erase this problem of contrast in your embedding. But it wasn't something proposed by the authors of Wasserstein pooling layers, but it's something that I included for them for fairness in the benchmark for TFGW. And well, the problem didn't happen in a sense. So that's for for contrast lighting. That's my two pieces.
Okay. Thank you. And maybe a very last quick and maybe a little bit open question would be regarding so interpretability of, for example, in the dictionary models. I think one big problem in all the Romer-Wasserstein work, for example, for computing centers or dictionary, is that every time you, in fact, learn a C matrix by imposing very few constraints on it, so like positive and symmetric, and there is still no, I think, very good options on adding constraints to the, I don't know, some graph with some constraints like a block model. I don't know, I say nice things, but do you have maybe some ideas on how to learn something that is meaningful, that is maybe more interpretable, to have constraints on the C matrix while learning it?
So more interpretable in a sense, I don't know. Maybe something that can be quite relevant for graph learning could be to constrain the set of atoms to be like Laplacian matrices, for instance, where you know that in the end with our models or the computing of GWD barycenters, you will preserve this Laplacian matrix aspect, meaning that you will still have the a weighted sum of these remains like a Laplacian. And but I don't know if it will be more interpretable. One thing that you may think about also would be to try to design, to learn from Euclidean distance matrices. So for graphs, you can actually derive from the adjacency matrix what is called the CIF distance, CIF representation, which is give you a distance matrix. It doesn't help at all in terms of in terms of interpretability. I think that the adjacency matrix anyway is the best. But like in terms of learning process, if you are able to constrain or to see that you iterate over the graph atoms, also Euclidean distance matrices, so you end up by solving GW problems which are concave. So it can help you actually more in practice. That my intuition, maybe it's wrong, but if your problem is concave, you will end up faster. Maybe just locked into a corner, but maybe it can be a good one. And so that could accelerate the learning process of all this algorithm. And well, that's all the thing I thought about, but I didn't get didn't really do experiment in this yet.
Okay. Well, thank you for your comments and the works, and I really enjoyed a bit sad not to be here today. Congratulations.
Yeah.
Thank you.
Yeah.
Thank you.
Thanks a lot. So, I think it's time also to see whether there are any questions from the audience. Before I make some questions myself. Just wonder if anybody wants to make comments or questions. Okay, so let's see. In any case, if it is not the case, I have only a few questions to Cedric. First, a comment. I just would like to share the comments of people we were previously posing questions to you. I do subscribe. This is really a very nice piece of work. So I think this is I enjoy being here this afternoon. Very nice discussion. Of course, I would have preferred to be directly there. Unfortunately, I couldn't come. But yeah, thanks a lot. So I have primarily curiosities concerning the intersection between what you've been proposing and the more traditional neural computation. I very much would like to say that it's refreshing to see something where there is some important foundational contribution in the area of graph neural networks, because after the previous the introduction of graph neural networks many years ago, and after the more recent interpretation in terms of convolutional graphs that we have mentioned, we haven't seen lot of progress. There is this interpretation on geometric learning that I very much like what you presented today. One question has to do with the kind of potential usage of the theory. You have been mostly focused on what I call graph collection, right? So essentially, you propose a theory where you do assume there is a graph collection, and then you think of number of tasks on graph collections. But I just wonder if you can also think of something different, where you do have just one graph, right? And you want to make inferences and decisions on this graphical domain. Just to give you a very quick example, think of a social network and think of decisions and kind of prediction that you may want to take in this graphical domain. And of course, I don't think I need to add any comment on that. Of course, it's not a graph collection, right? It's a unique graph. And so just wonder what is your comment in this case?
Yeah. Thank you, Marco, for your comments. Yeah. So if I understood correctly, is in a sense, what we do, does it can be applied in a sense to node level tasks instead of graph level ones, I guess. And yeah, that's correct.
Yeah.
Yeah.
I think of simply, for example, a social network. You want to make decisions on this graph environment, right? So it's not a case that you want to classify apps or you want to make predictions on single graph, but you do something different, right? You want to take a decision like, for example, whether or not this person will likely be a friend of you or will likely earn a certain amount of money at the end of the year, right?
Yeah.
So any time the decision based on the profile of the person, the kind of connections that you have. Of course, there are plenty of problems there. You can think of a graphical domain, right, where the information is located, and then you want to take decisions, right? It's something different because you take it on the basis of characteristics of your graph, right? So the decision is associated with single partnerships, right? It's not a decision on the graph because you have just one graph, right?
Yeah.
So essentially, it's a special case that this big graph becomes disconnected, but it's a difference, right? Because that you are interested in taking decisions on a collection graph. So that's the spirit. I understand that this is not quite common at the moment, right? Because if you look at the literature, especially the literature that we have mentioned, graph computation networks are not very adequate for this kind of solution. But originally, the kind of graph neural networks that were introduced were based on relaxation mechanisms on graph neural networks. which make it possible to implement kind of computation. So I just wonder, using optimal transport, what's your interpretation of this problem?
So there are actually many ways to define a kind of transport distances over a graph, even over a tree or stuff like that, that are not really directly correlated to what I did, but so it changes and complicates a bit the problems, but meaning that you can compare distributions that lives over a graph. And for instance, up to compute a barycenter, or to also perform a dictionary of this space, this graph space. So a dictionary could help you like to identify, let's say, communities within this graph too, just by performing barycenters by a transport problem which is defined over a graph. And I mean, it connects to many things that we did with the semi-large GW, but it's a bit different from what you asked. But it's true that in spirit, anyway, a transport matrix is a joint distribution between an input and an output. So you may define node embeddings, subgraph embeddings, just by looking at entries of your transport matrix. Like for the node I, you can look at the transport matrix, the line, the if row of your transport matrix. And so that may be a way to go to a decision making at the node level for any graph. Also, you may think about extending what we did just by sampling, in the sense that if you have a big graph, you may try to actually embed any subgraph by GW distances to very small graph atoms. So it will give you like a kind of collection of subgraphs that may be useful for prediction at another level, in a sense. But maybe I felt like your question was going a bit further than this. So,
I understand, because your thesis is actually on a different subject, right? It's only a question of perspective, because so far you very well define the setting, and the setting is one of collection of graphs. Whereas this is a bit different, right? Because it's not a collection of graphs; it's a unique graphical domain. That just stimulate your curiosity about how this methodology, very interesting methodology, optimal transfer, can be potentially also face this kind of problem.
But it's also quite related to what one thing that I put in the conclusion of my manuscript, and also briefly introduced in our discussions, was that anyway, if you are using like solvers, which every steps are fully differentiable, optimal transport solver where every step are differentiable, you can use the transport matrix as a feature, in a sense. So you can learn directly from this. So from doing so, you can perform node-level tasks. It's just like, for now it hasn't been tested, and I think it deserves a lot of, it should be tested quite soon, in my opinion.
Another quick curiosity concerning one traditional question that is posed in your computation, right? The one of the capability of approximating this function. So once you're in a selection of graphs, one question is, how can you let's say, provide using this computational scheme some let's say guarantee that you have the possibility of having in the framework that you're using. I just wonder if you consider this issue of how accurate this map at the end is.
So, well, using the solvers that we introduced, like conditional gradient, etc., and so we saw in non-convex settings, the errors, unsure to converge to a local optimum. Not a global one. That's why also like with Florence, we said that, yeah, we are lucky, we found a good local optimum. And in practice, it happens quite often, apparently, looking at the results in the end. So we have this kind of guarantees. We don't look that further over the guarantees that we may have for instance, the graph dictionary learning processes. In this kind of stochastic gradient scheme, I mean, with a projected gradient step at the end, one thing is that if there is a transport matrix which is inherent to a forward pass, let's say, you have to know that you are actually computing gradients by backpropagation, for instance, for the GNN, which was preprocessing the node features beforehand. You have to ensure that you have a local optimum for the transport matrix to compute these gradients. This is related to the envelope theorem. And overall, for the global objective, we hadn't like real guarantees on the convergence. I think it's rather easy to, I mean, Vero proves that if we solve this using block coordinate descent, for instance, graph dictionary learning approaches, if actually like papers on block coordinate descent algorithm that gives you convergence to a local optimum. And so I hope that answers partly your question.
Just to get back to curiosity, since you were mentioning this local minimum, just curious to hear from you if you have considered what is the actual mechanism facing this problem, right? If you regard this problem as relevant or let me be more explicit. In the community deep learning, for year and year, the issue of optimization and the corresponding discovery of a suboptimal solution was regarded as important. At the end of the day, we discovered that it's very important to speak in neural networks and the problem, amongst others, the problem of local minima magically disappear. So I just wanted to have a comment in the overall optimization framework that is connected to your studies about what is going to happen when in front of local optimal.
Well, it's very hard to say in the sense that anyway, all the problems that we are tackling are NP-hard. So, like hoping for a global optimum is like a fairy dream, I guess. And my opinion is that it clearly depends on the solvers in the sense that you have a clear reflection to have considering regularization, like promoting smoothness, differentiability of objectives, etc. And this can really change the game in practice. Even if for these settings, in non-convex settings, you end up with optimum, local optimum. If you induce more smoothness in your global learning system, it may help, depending on applications. But, well, that's all. So.
I think it's fine. I think that we started to pose questions to 45, and well, I think you reacted to a number of questions, which is like to say you defended your PhD. And I want to say that again. I think it's really not work and design to invite the advisor, the people involved in the advising to this, because we did very nice work, but I'm confident that you are want to say something. So, Remy and Marco, we have
Thank you very much, Marco. Okay, so it's time for the supervisors. So not so many words for me. I just want to congratulate you. Not really now in a while maybe, but by the way, your answer to so many questions and your presentation was clear as well as your manuscript. So I just wanted to say that it was a really pleasure for me to work with you during these 3 years because, as you will remember, this thesis started in some conditions which were not exactly the most desirable ones because of the pandemic. So here at the beginning, so the first year it was a little bit cumbersome for everyone. I think that later on things started to go in the right direction. So you have always been very passionate to research, to mathematics, document transfer. This is something that you already have. At the beginning, you just need to be guided a little bit in the right direction in such a way not to lose too much of energy in so many things, and we try to do it. But apart from this, you did almost everything alone. So it was a pleasure for me to stay with you and to campaign and hope you during these 3 years in a reasonable manner. So thank you very much and congratulations.
So it was late. So congratulations. It was a really nice presentation. It was really nice to read your manuscript several times. It was my job. It was really a pleasure to have you as a PhD student. For those who don't know, Cedric contacted me a bit late because of his engineering school that makes weird decisions about internship dates. And so I was really lucky to be a part of the Troisième École d'Azur because I could. I had a funding for him, and we started in January. In January, I had medical problems, didn't see me for 1 month, and then COVID struck. We wanted to send him to see people in the US and everything was cancelled. It was kind of a hard start, and you still managed to work. In my opinion, I'm totally biased, okay, but you have really very interesting results. And you did very well. You now present very well, which, I mean, your first presentation in front of people was awful. And now you are a very good public speaker, so and this is all you, okay? And just, it's very innocent on the slides, all the rest is you. So that's congratulations on that, congratulations on your results. I think you never got rejected in the machine learning conference. So I'm not sure it's gonna last, but that's crazy, okay? Being accepted at first position, all your 3 papers, that's a very, very big achievement. And also the oral at NERIPS, that's not nothing. So congratulations. So the real pleasure to work with you. I'm sure you're going to be a great researcher in the future. So yeah.
Thank you.
I'm done. Thank you, sir.
Thank you, René.
Okay, so I think it's time for the committee to meet, right?
Yes. So I sent you a Zoom link.
Yeah, we have the link for the committee. I guess we can let this session open, right? Just
Yes. Okay. See you.
See you on the other room.
Yeah, in 5 minutes.
Je fais pas Je vais dire le
Tu laisses comme ça, parce qu'on a cette ça ensuite.
Tu les as pris? Enfin, le fait d'en parler. Ah. Il y a combien de
Non, oui, c'est chiant, mais ça donne une visibilité
Oui, dans la boîte. Ouais, c'est ça. Et surtout, on est un bon chauffeur.
Après, des ressources, ouais, des ressources, quel genre de ressources tu dois choper? Des gens, ah oui, pour développer les trucs.
Ouais.
C'est la première fois qu'elle va participer.
Ici, on a beaucoup qui partent à la retraite.
Ah ouais,
Au début, elle a commencé à
mais ça,
passer à.
ouais, oui, si, c'est dans la vie, mais ça, c'est plus un tamarin, peut-être une autre. Ouais, sinon, c'est au-dessus de ça, la sécurité.
C'est les gens-là qui viennent le compte. C'est eux qui vont les budgets.
J'étais avec le tablette, ma collègue qui a commencé à
Il
parler.
va finir sa thèse en décembre. Et lui, il aurait aimé que pouvoir continuer sur le conseil à ce sera là. Et Thierry, il a dit qu'il avait essayé de commencer
Ma collègue,
en gros, au-dessus, il a mis des jolis trucs.
Ah, oui,
Alors que eux, il est en retraite. C'est à 4 pôles, tu vois.
ouais. Ah ouais, bah, sinon, c'est important, les projets, bah, le projet,
Et après,
je vois, quand c'est sur le ouais, c'est sur place. Ça développe les cas, mais non, non, c'est vraiment pas. Peut-être que tu peux ça passe le truc entre deux. Ça peut.
Ouais, non, mais sur le truc, il faut c'est pas
les postes
non, mais non, même pour moi.
oui,
Il n'y a personne.
il est passé, il y en a un qui a
Comment c'est un peu basé sur les animés et il y a un deuxième programmeur qui a aussi passé un peu. Il s'est fait par un pasteur, voilà, mais ça jamais se fait.
Ils sont un peu de temps pour le terme.
Ah, c'est même moyen. Regarde sur l'actif avec des moments. C'est la plateforme. Ça marche. Ah oui, c'est vrai. Parce que j'ai été avec le voile pour ces enfants, moi je suis bon choix. Non, je pense que je vais dire. Non, mais je pense que j'étais à la finance, c'est les 2 jours où je parle avant 18h30. Je fais des bons de 20 18h30. Là, c'est ça va être pareil. Pensez qu'en écoutant une deuxième fois, je comprendrais mieux. C'est pas pareil. Mais c'est pas grave, c'est cool quand même. C'est pas la présentation de problème. Non, c'est cool.
Non, moi, la présentation, j'ai fait super. Moi, j'ai pas de confiance, mais j'ai fait, je veux dire, sans le manque de connaissances, en tout cas.
Ouais, c'est ça.
Voilà, c'est ça. Et les slides, ouais, c'était bien. Genre, mais le graphe était beau. J'ai surtout admiré aussi de faire un graphe comme ça, avec le bulletin en haut.
Et sur la...
Désolé, c'est pas le truc, c'est le truc, j'ai le truc, je sais pas.
C'est bien, il grave, c'est avec un qui est aussi.
D'ailleurs, sur la web diffusion YouTube, il n'y avait pas les slides. Moi, en Asie, il n'y a pas les slides, heureusement qu'il y a une belle je ne dirais pas qui c'est.
Ouais, c'est lui.
Ah oui, il y avait pas.
Ouais, c'est lui. Bah, je vais laisser, tu vois.
Oui, c'est chiant déjà.
Sinon, je vais faire un truc, je vais faire l'audio, essayer de profiter.
Ouais, j'avoue ça.
Déjà, c'est bien. On va faire l'installation. Ah, mais non, aussi. Le gars qui a installé le. Enfin, en gros, lui, c'est vrai que ce bâtiment, normalement, il était fermé la thèse et ça faisait chier.
Est-ce que c'est un des mecs de la DSI qui fait ça? Il y a un mec qui ne sait pas très bien
Je vais pas en parler dans le détail. Franchement, je vais venir la cam.
Non, je sais pas. J'avais envie de te dire, il y a une après-midi. Ouais. Non, ce sera un autre point. Bon, ouais, ça va être bon. On partage avec la famille. C'était YouTube, vous savez. Je vais demander, vous avez aussi des slides et non, je
La production sur YouTube, c'est toi qui voulais le faire.
ouais, maintenant, tu vois, il y en a une trace, tu vois. Ouais. Ça va plus suivre moi.
Parce que j'ai l'impression que tous les contenus, c'est ça. Non, je veux dire, pas une volonté de diversité,
Moi, je me suis dit,
C'est ça, ouais.
ouais, donc, c'est
moi j'ai pendant le projet, est-ce que tu faisais tout audio? D'ailleurs, c'est enregistré.
Ouais,
On l'a pas mis dans le
ça j'ai pas donné ça.
Tu as dit que tu n'avais pas vu ça pendant ta présentation?
Ouais, c'est
Moi j'ai vu que les questions sur YouTube et aux étudiants, vous avez plus ça comme
Pourtant, j'ai fait le truc. Je faisais partage de mon écran, sachant que c'était l'écran Zoom. Donc, tu vois les jeux et les slides, plus moi de l'idée. Je sais pas, comment ça va marcher?
Tu disais que tu faisais un peu de vélo aussi, que tu prenais un peu quelque chose de vélo?
Non, c'est Rentaigne de jury.
Ah,
sur un séminaire national.
ah oui, oui, sur le même.
Pas sur le truc.
Sur le jeu, sur sa gueule. C'est du même site.
C'est dit qu'on avait suffisamment de problèmes avec les marques, on parlait d'une chose.
Ça, je vais prendre ce soir.
Bravo.
Non, a priori, bravo.
Ciao. Ciao.
Tu n'as pas pu avancer.
Un bel, il y a moi, ce choix, et je crois qu'il en commence à développer tout ça. Voilà. C'est facile. De toute façon, je crois que ça va tous prononcer. Ça dépend de qui prononce pour.
En fait, ce base, nous, on appelle en vrai, comment tu fais. Voilà, ils ont un vecteur de pratique, genre une distribution des normes, et le centre, ils ont mis à part. En fait, la classe, elle est déjà là. Et je vais prendre dans je crois que non, mais
Non, je voyais que c'était.
Et en fait, c'est pas Et en fait, tu peux en gros, tu ah, je sais, il est dans
It's like the one with one is they describe
big duck.
yeah.
This is power here.
Actually, the director of the center right now. Nice promotions.
Est-ce que tu, comment tu sais dans quel domaine aujourd'hui usually, quand est-ce que tu as su dans quel domaine comment tout ce qui se passe?
Ça dépend d'un film de manuscrit, d'un besoin c'est dans le milieu de la manière
Then they also have like friends like outside the film. No, like you said, I don't care. You just so I go them try to quantify.
J'étais là pour la présentation, mais je pense pas que tu ça, c'est les questions de Noé.
There's a very high chance if you were a king, right?
Je sais pas, je sens que des doigts. Tu l'as enfermé dans ton bloc. Ça la championne là? C'est une championne, ça.
So can we see that it's you? If you go in front of the so we can do it. No? No, you just thought that. Comment ça marche?
7.3.
Tu dis ça va délivrer. Tu dis ça va laisser une double pour le délivrer.
Fuck.
Bravo.
Voilà. Ça, c'est bien, comme ça, il est rond.
Did you get?
Oui.
Ah oui, d'accord, c'est assez drôle en fait, la liste.
He said, what was it? Did I and then like
On n'est pas trop ici. Mais oui, je pas ça, il
Ah, c'est même pas signé. Bravo le sang. Bravo le sang. C'est
juste le son ou le son de la messe?
c'est bête.
D'accord. Parce que le son de la messe,
the two free
je sais pas.
as you were
Et le son du vaisseau, c'est petit.
it's like
C'est vraiment pas un complexe.
well, like yeah, you rub it in the blood, like the same as it's like not something you really from it comes from yeah, kind of
C'est vraiment ça qui est écrit programme docteur.
j'ai rien.
Ah bah il fait un truc.
Tu veux que j'ai une question?
Bah,
Ah oui, mais rapidement.
si c'est pour écrire bravo, je vais écrire par-dessus Hugo. Ah oui, bravo, mec.
Ça va, tu veux la C'est énorme.
C'est toi qui commence.
Non, c'est vrai. C'est vrai que tu as froid dans ton bureau. Je comprends pourquoi tu es là.
Ça avance, ouais, j'ai parlé avec lui.
Ah, et là.
Et alors, ça non. Non, mais si, parce que là, il y avait un enchaîné quand même. La réaction, ça va dans le calme. Et je me suis dit, en fait, c'est connaissance. Mais sinon, j'ai avancé de ouf. J'ai un peu senti dans l'esprit.
C'est bien.
Ouais. Et du coup, en fait, il y a plein de degrés qui permettent de bosser assez rapidement des degrés qui font partie de son.
Ah, c'est bon.
Ouais, Torchido, Moonlight, tout ça, et ça permet de. On a un peu de pipeline. Je le mets tout à vous. Il faut vraiment que j'arrive à me limiter à faire ici. Ouais. J'arrive pas. C'est une question de clé je sais les convertir très souvent. Ouais, c'est pas une bonne idée. Ouais. Je peux faire ça. Je t'envoie le fichier lié à ça et je peux le convertir. C'est bien. Ah, t'as accès à ma net? Son net, vous voulez que je vous clique avec la clé? Non, mais que je te donne accès à ma net. Tu vas me comparer? Très bien. Très bien. Non, mais voilà, c'est. Il est facile, donc je pourrais rien vous faire. C'est SSH qui.
C'est vrai. C'est vrai.
Vous faites un moyen technique, ouais.
Mais c'est hyper bien.
Ouais. Non, tu y as
Bah, limite, je la garde.
la carte.
Aïe.
Je sais que t'avais des petits.
Bah, je sais pas, je m'en viens là, parce que ça se trouve, la délibération se fait je sais pas où.
Non, ça serait là, d'habitude. Bon, c'est un peu dans la gauche. Je vais voir en bas. Voilà.
Je sais pas une place.
Ah ouais. C'est un projet.
Why do you want to use Python?
Ouais, non,
Why not the shell?
Because with the shell, you have like
Yeah.
it's paid, yes, and I have like a 300 giga.
Oh shit, yeah, okay. Never mind. Yeah, okay.
You can do that, but like if you have like a connection program, you have to start again. That's crazy that you can start.
Just say don't replace the stick.
This is my connection programs. In supervised engineering. And supervised engineering. Wait, just hands.
I use Facebook, that's why I'm asking. I have to send 20,000 images. I think by Bayesian, I guess.
No, you can't. It's already easy. Really? It's 300 giga. It's a mega image. X3D images. The images. Et on se lève là. Ouais.
Ça.
Ouais, peut-être quand même. Non, c'est pas.
Ouais.
On verra.
T'avais pas trop temps, enfin, ça va pas bien.
Non, parce qu'il y a hier, j'étais en voiture.
Oui.
Je suis sport. Je suis cardio. J'avais dit non, et après, ce matin, c'était cool parce que je me suis réveillé, je me suis dit,
C'est bon.
if you want. I'm changing.
Allez, il va accepter les gens. Donc, tu vas lire le rapport, et après, tu vas lire le truc. Il faut que je repartage. Oui, tu repartages tout.
Parce que j'avais plus trop de batterie.
Putain, il faut qu'il puisse parler.
On n'a pas pu. Il y a des problèmes pour retransmettre les slides.
Je sais, mais ça va marcher, on s'en fiche.
Non, mais si, je le ferai après. En post-processing, je le ferai.
Fais ce que tu veux. Là, active-le, accepte-le. Tu les acceptes sur Zoom? Ils sont revenus. Marco, can you speak?
Okay, we can't hear you. Activez le micro, s'il te plaît, Cédric. C'est ce que je veux.
Marco?
Yeah, but this one is mine, so it's another problem.
Yes, but it's just to tell Marco that we can't hear you, unfortunately, Marco.
Il a activé son micro, donc c'est un souci là. Qu'est-ce qui se passe?
Ah.
Okay, we can't hear you.
Titouan,
Vas-y.
can you say a word, maybe?
Attends.
No, we can't hear you neither. No.
Okay, so that of course nothing is working. One sec.
It's the same problem that we had at the beginning of the afternoon.
Tu fais quoi là?
It's not your problem.
We can hear you now. That's good.
Okay, great. So, Mr. Vincent-Cuaz, the committee has scheduled to analyze your PhD thesis and the defense and came up with the following report. Mr. Vincent-Cuaz presented in a pedagogical and dynamic way the completion thesis
are the interface between machine learning, graph theory, and autonomous transfers. Given the large spectrum of these results, he managed to distill the essence of his main contributions for a beautifully illustrated presentation. He applied very well to specific technical questions as well as questions involving the perspective in the future of the field. The discussion with the jury touched a number of many perspective and extension suggested by this work. It has answered the many questions very convincingly, showing a perfect mastery of the subject, of the underlying theoretical tools, as well as of the applications issues in artificial intelligence. The jury is convinced that this is an excellent thesis in every respect, both in terms of the diversity of the contribution and the elegance of the results. It brings new perspectives on graph neural networks. The proposed optimal transport approach is a refreshing methodology, which offers very interesting new research guidelines in the future. The jury also appreciated the effort to disseminate the results with good quality and open source tools. For those reasons, the jury thinks that Vincent-Cuaz has all the qualities to be an excellent scientist. The jury unanimously awards him the degree of Doctor of Philosophy of the University Karlsruhe and sends in congratulations. Okay, so now next step, I'm confident we will have good opportunities for postdoc. I think you have
He's going to read the.
I think I have to read kind of sermon for scientific integrity, which will be in French because no, it can be in English. It's fine. So, in the presence of my peers, having completed my doctorate in doctorat sciences pour ingénieurs, and having thus practiced in my quest for knowledge, the exercise of demanding scientific research by cultivating intellectual rigor, ethical reflexivity, and respect for the principle of scientific integrity. I commit myself, for what I will depend on me, in the continuation of my professional career, whatever the sector or the field or activity, to maintain an honest conduct in my relationship to knowledge, my methods, and my results. Well, thank you. Truly, thank you for all your words. It's really an honor to have defended my PhD thesis in front of all of you, that I consider as models in research, actually. And well, I hope that I will keep up the expectations for the future. And well, then I guess I can have more private words. I guess that first, really thanks to my supervisors. It was the beginning was a real struggle. It was I don't know, trying to really hard into the subject, in your cave and alone under everything. And actually, Remy he gave me this feeling of being excited about an idea, which pretty much makes everything related to research looks like games, sort of video games that are quite addictive. And I think it's a strength. A balance has to be found for personal matters, but a balance has to be. it's a great aspect. So very thank you for this, for everything to YouTube. Marco has always been a support in all this. Like playing bad cop and good cop with Remy was like, it was really nice way to balance my way of thinking, and also well, it was nice. So, and then thank you for a long time also to be here. Like it's an honor after after studying that much of papers and all. Then thank you to my family to be here. Nothing could have happened with. Maybe I will switch in French. Sorry for this. Merci vraiment à vous tous de ma famille. Clairement, en fait, ça aurait pas pu se passer pour maintes et maintes raisons si vous n'avez pas été là. Enfin, tous parmi vous, probablement c'est toi, maman, qui a pris le plus de revers de bâton de ma part de fils ingrat dans certaines circonstances où j'étais un peu sous pression. Mais ça, enfin voilà, sans vous, ça serait pas passé comme ça. De même pour ma sœur qui n'est pas là. Et ces petites filles qui, en fait, toute cette belle famille me motive à aller de l'avant et à défendre mes convictions et ce qu'ils font, et ce qui fait que je pense que j'ai de la force pour faire de la recherche, avancer dans ce domaine, sachant que il faut se confronter à des hauts et des bas de manière assez régulière. Then for my friends from Maasai, all my colleagues, it has been so much fun to be with you, so much support coming from everywhere, and thank you for everything. Quite well. It's and a very last word, which will be like for someone that can be here actually, but was also someone motivating many things inside me, which is my father. So, big up to you, Daddy. Thank you. Well,
Okay, so on behalf of Julie, our best wishes for your career.
Thank you to everyone. Bye. Bye.
Thank you, everyone.
Goodbye.
Goodbye.
Thank you very much.